Hello, students. So, finally, CSIR has announced a date January 29th. How much time we have? 2 months? What can we do? Can we crack? Yes. Why not? Let's give it a try. Well, I know that in this COVID situation, I also have lost my energies. You also lost. But well, when it's time, we need to give up all our lethargies, everything, and get up and fight. Let's do. So here is an online crash course. I will try as much as I can. I don't have a detailed workout plan, so I don't know what we can be able to do at the end of the day. But we will try. I will try. Don't think me that I'm a teacher. Just think I am a student, just like you, just as your friend, just as your friend. I'm your friend, right? Okay. Those who attended my classes personally, so he or she will know. Well, I'll speak English. The class is online, means not a live class. There will be videos just like this. This is a pre-recorded video. I record it and then I upload it into. I will send links in the Google Classroom. In the YouTube, I can upload only videos. The slides, assignment, I will upload in the Google Classroom. The classroom code is this written here. I can increase it a little bit more. Then what we'll do, let's see what we can do. Fees, well, don't think about fees right now. That's 2-month initiative, so I'm not asking to deposit fees. Just join in the Google Classroom. You may not join in the Google Classroom also, you just watch these videos in the YouTube. So I'll keep posting in my channel. Just my channel is just my name also. You'll get it. Well, let's try to write something. This is a whiteboard. This is a board. Okay. What we'll do in this board, I write with my pen tab. So January 29th, this is the day. Well, we need to crack. My English is not that good. Well, this works. The format of the CSIR net, I assume it will be remain the same thing. So part A, part B, part C. In general, it is a aptitude. You know, just a quick reminder. These are basic in general, not necessarily to be basic physics. You know the syllabus, right? My handwriting, I can write in a better handwriting, but well, to write it first, I need to be first. So we start with classical mechanics before you know the syllabus. So I don't go to the syllabus, I go directly to mechanics. We start with mechanics. Is my recording is on? I need to check it up. Yeah, my recording is on. So mechanics, we have two part in general. That is Newtonian we divide, and that's Lagrangian and Hamiltonian formulation. We have questions from both Newtonian and Lagrangian formulation. So it's not that you only read Lagrangian or only read Newtonian. You read both. In your BSc, I know you did not read much. I know whatever you read in your class 2, I mean in class 11, 12, you also forgot. But that does not mean that you don't read anything. What we do with Newtonian. The ideal way is to just start from X. Verma, but you won't do that. You have very less time. So what is our strategy? Our strategy for all the subjects will be do as much problems as you can. So we divide it a little more. Some very basic concepts like Newton's laws, just little bit of kinematics, etc. This momentum conservation, energy conservation, etc. Second part will be like angular momentum. Then there will be rigid bodies. I just write this to just keep you, just bring you in the trap a little bit. Well, rigid bodies, some small oscillation. Then what else? Coriolis force, non-inertial frame. There are other forces also, centripetal forces. So general shear frames, etc. What I have here, I have the problems of previous years rightly ordered for you to practice. I uploaded this in my in this Facebook group, in my personal pages before that. I hope you already have or you downloaded what I guess, but didn't practice at all. So let's show you. I have this problem sorted. I worked with my student Sandeep Biswas. He's a very good student. So we both worked it and formulated it. We have these problems: Newtonian basic Newtonian mechanics, angular momentum. Today we'll be restricting ourselves in this. We have central forces. I should not forget that. This may be a part of the, sometimes it read with Lagrangian formulation, sometimes Newtonian formulations. So just we have these problems. So what are here? We have divided this along with subtopics. So we have dissipative forces, we have basic kinematics and dynamics problems. Here we have this oscillatory problems, just like simple harmonic motion. You read it in this way. Momentum problems, momentum energies, all this. The rocket forces problems we have here. We have almost everything till June 20, not June, say 2020 get up to this. We already worked it out. 2020 November net, it's not included. 2021 gate is not included here. So we'll keep including. It's a rigid body angular momentum. So we have simple concept. Simple motion of rigid bodies, angular momentum, these are, I divided it into subtopics. All these are problems. We have hints and solutions, but that is less important than your workout. You need to work it out. We'll discuss it. How to work it out, in which strategy. I'm just showing you the Newtonian mechanics. We need to solve this. So we have moment of inertia, principal axis, and rigid body dynamics also. Non-inertial frames we do have. So what you will do, Say we start with dissipative force problem. Just start it. We have jam problems, gist problems, TIFR problems. I gathered all the problem from all the previous year's problem sets in a syllabus wise, topic wise, ordered format, in a ascending order of difficulties. We tried as much as we could. There are scopes of improvement, of course. So here, say in this topic of dissipative force, like when there is a like minus kV type of force, minus kV square type of force, these problems are there. So you need to work this out. We have in net also this problems appeared. So don't ignore this. This comes. So we have 11 problems of this dissipative force. Try yourself first. We have answer keys. We have hints little bit. These hints were prepared by both me and Sandeep. We have solutions also. I don't claim that all topics I can give you solutions. As you know, we have solutions of mechanics, quantum mechanics, Newton mechanics, overall classical mechanics, quantum mechanics, stat mech. These basic topics we have solution, mathematical physics and thermodynamics and stat mech. I could not work it for this atomic and solid state also. We have hints, we have answer keys, but detailed solutions are not available for nuclear particle, solid state, and this atomic and molecular. So, well, we'll see what we can do for these topics. I don't think that you need solutions, but still, if you need, you can go through the solutions. You can try, but my suggestion will not be to go to the solutions. So after we finish this dissipative force, we have basic kinematics and dynamics. That's plus 2 wala type of problems, but we have different problems. We'll discuss it out. So these are some problems. You need to work it out. We again have answer keys and hints, and these answer keys are 99.99% correct. My experiences made them correct, but still, if you find a mistake anywhere in the answer key, please ask me. Please ask me that we're getting something different. Right? Okay, we have all this for you. So this will be uploaded in the Google Classroom. No issues. That's okay. So we have this for oscillatory motions, momentums, angular momentums, rigid bodies, etc. So you need to work it out. Okay. So in our whiteboard, once again. So for the Newtonian mechanics, we have dissipative forces and basic. I just keep reminding you the basics of mechanics. What are the basics of mechanics? Force equals to ddt of momentum. That's the basic of mechanics. We have concepts of inertial forces. Yeah. We have concept of inertial frames. Yes. We have concept of energy conservation. We have concept of momentum conservation. Yes. These are the mechanics. So, inertial frames, momentum conservation, and what? That's fine. That's fine for a good start. So, the very first place we do with constant forces. constant force problem, that is constant acceleration problem. If force is constant, mass is constant. Mass is not always constant, we'll do variable mass problems. Okay, constant force, constant accelerations for this type of problems, free body diagrams. You know all this. You may not know, just have a little bit of revision from books like A.C. Verma or Disney Halliday, like this. So you go through this, then just kinematics formulas, just check, but you just check it. You might have forgot something. There's S equals to ut plus half of ft square, v square equals to u square minus 2fs. So you might have forgot, but you should not forget. This two-dimensional problems like this motion of a brass, sometimes say it. Then sometimes we check the problems. Dissipative force, you may start at a second stage. First, you may start with basic kinematics and dynamics. These are very easy problem. I sorted it out. This radial velocity, angular velocity, you know angular velocity, right? I'm sorry. So these there is something called angle, so that you know. This is theta, this is s, this is r. Divide, just take derivative with respect to time. ddt of s is ddt of r theta. If your r is constant, the motion is going along, so v is r omega, like this. Alpha angular acceleration is, no sorry, linear acceleration a is r alpha. Fine, these are there, and then same formulas of kinematics that will do these problems. This polar angle and polar angle, I should not say it, motion in a 2D plane. There is a formula of this radial velocity, angular velocity, radial acceleration, angular acceleration. You remember all this or you forgot? Okay, I may show you something. This is my notes also, this also I uploaded. So remember something? This is dimensional analysis. I tried to write a detailed book of mechanics, but still I could not finish it, as you know. These are some concept of basic two-dimensional motions. So you can read it from this notes, you can read it from any book you want. We have very less time, so I'm not teaching you directly in the whiteboard. So these are the r's and thetas written as in terms of i's and j's, unit vectors of polar in terms of unit vector of Cartesian. So we have all these formulas. So the velocity and acceleration in a plane, polar plane, acceleration as a whole, acceleration formula. So what is the summary? Summary is, in polar you have r cap and theta cap. your direction of unit vectors are not fixed. In 2D polar, r and theta, of course directions are keep changing. Here the direction is in some direction. Here if you go here, your direction of r cap will be in this direction, theta cap will be in this direction. R theta directions keep changing. So first you need to know how to write this r cap and theta cap in terms of I cap and j cap. Of course a little bit geometrical argument will give you this. So we may have a snapshot. That's good. That's very good. Then we may have ddt of r vector as r dot r cap plus r theta dot theta cap, linear velocity and angular velocity. That's done. And you should remember this acceleration. Which acceleration? This is the formula of angular, means sorry, not angular, means the total acceleration. The acceleration d square r dt square, that is general acceleration formula. We don't have much space here. This is above my head, I guess. Little bit above my head. Good. You know these things, these problems can be done. This problem will involve the solving a differential equation. That will be seen that this will seems to be a coupled equation, but take double derivative, you will get it. No issues. This type of problems are called a trajectory type of problem. So just square it out and you will get this. That's very simple problems. If you don't, and check it and the solution. This is an what is this? This is just a collision problem. So we have a collision problem, conservation of energy and momentum, elastic collision, both momentum and energy conserved. Inelastic collision, only momentum conserved. So just check it out with collision problem. If you forget, then please keep revising. This is elastic problem. This is again elastic collision problem. This is just +2 problem, perfect elastic collision of two identical balls. Most of you remember that the angle between after the collision is pi/2 among these two particles. This is standard +2 problem. You can always take a pause in the video and look at the problem. This is again a collision problem. Conservation of momentum, energy will be there. No, stick together, that means stick together means you guessed right. No conservation of energy you can apply. Sticking something, either it will be said that it is an elastic collision, just like this, or that. Elastic collision, it will be shown as, it will be mentioned as elastic. It will again mention at elastic. Just for this bookmark, it is not showing properly. It's elastic, but in an inelastic collision, you might not be mentioned that the collision is inelastic, but something stick, something get into it. This will be a perfect example of inelastic collision. Well, is it okay? My position. Yes, fine. This will be an inelastic collision. So for inelastic, you might not understand what, if it might not be mentioned at inelastic, but yes, something sticking together, something going inside it, inelastic, only conservation of momentum. This is again this is mentioned at inelastic, so you just keep applying this conservation of energy and momentum here, and let me know if able to get these things. This is a collision with coefficient of restitution. You remember the coefficient of restitution? After the collision, the ratio between the after collision velocity and before collision velocity. If something is going to 1 meter and get a collision, boom, from a wall or something, and get it back with velocity 0.8 meter per second, then coefficient restitution will be 0.8. So well, I'm trying to just have a feeling that you have studied it before, so you don't need to go through all the books. You don't have time just to go through the problems. Take a hint, listen my lecture, what I am telling a particular thing. Just check any book or just check the solution. You get the idea, right? Have a mechanics book in front of you, both class 2 level and graduation level. Then you will be getting it. You don't have time to read Goldstein thoroughly right now, so don't try it. There's a frictional problem, that's fine. There is a one tricky problem. This problem is very, very, very tricky. Look at the solution. You may get the answer 4n, but that answer may be the 5n. So most of you give a wrong answer. Don't argue that you are getting it right. Look at the solution. We tried to make you understand properly this problem. So this is a tricky problem. Please have a look. This is a crash course, so we won't discuss a lot here, all theories. So I'm trying to be a little bit innovative. This is again a little bit tricky problem, but yeah, it's not that tough. The depression, little bit depression, you get acceleration. Object is dropped on a cushion. You just keep pausing the video, right? I know that you need to keep paused, so you are not in front of me and you're not listening live. So just keep pausing. Whenever you see a new problem, just pause the video, read the problem, then go forward. In this problem, the depression of cushion will give you the acceleration. Then the constant force, you'll get it if you get that acceleration. That's my hint. These problems need a thorough discussion. This 2.13, 2.14. There is a tricky theory behind it. So 2.13, 2.14, 2.15, these are a similar level of problem, similar style of problem. Just have a pause and read the problem. You're given a potential and you are asked to find a time period. This is a classical concept of time integration from one point to another point. Do you remember that concept of this classical region and quantum region, the turning points, the points where the potential energy is the total thing, the velocity, kinetic energy becomes zero, the particle stops and turn back. So the classically allowed region in a potential. You forgot? Well, have a revise. Yeah, we have a blackboard, whiteboard. Do you remember this kind of things? Say I write the potential like this. This is my Vx, this is x. and this is energy. So your total energy is equating with potential energy. These are called turning points. When energy is potential energy. These regions are classically allowed region. Beyond that, your potential energy itself is getting higher than your total energy. So which essentially means your kinetic energy becomes negative, but that is not allowed classically. Okay, with this concept and integration, this will be solved. 2.13, 2.14, 2.15. We have it as in a solution. So this 2.13, 2.14. Let's get hand. Is it? The computer is not that old, but not that young. Ah, excuse me for this inconvenience. Inconvenience is deeply regretted. Yes, yes, yes. I don't know how many days I will keep my energy. Whenever I mention a problem, which problem set it is? It is Newtonian basic 1, like this. Under mechanics, each and every 0.1, so 0.1, mechanics 0.1. I sorted in this way: mechanics 0.1, Newton mechanics, like this. Like here, you see, this is notes, this is previous one. We have 5 topics here listed. So mechanics, under mechanics 1, 2, 3, 4, 10 files. Under EMT 9 files. There is another 10 also, but I will add it like this. We'll go. So well, where were we? We were here. This is also a +2 level of problem. You should get it. This is again a coefficient of restitution problems. You get it. This is a degrees of freedom. You know what is the degrees of freedom. Say if you are moving freely, just translation, you get 3 in 3 dimension. You are moving freely in 2 dimension, you got it 2. But remember the restrictions. Degrees of freedom is actually, say, the lowest number of coordinates required to express your motion. Is it remembering a generalized coordinate? Same thing, number of degrees of freedom. In harmonic ways you can move. So sinusoidal curve might keep you reminding of a 2-dimensional plane, but there is a restriction. You are not moving in a 2-dimensional, not moving freely in a 2-dimensional plane. So this is, there is a restriction, and the restriction, how can we express this just in a single coordinate? But what is your phi right now? So like this is 2.18. So I know you know this, but where are you? I just mentioned if I start theta from 0, I just mentioned the theta and I mention your precise coordinates. Is my recording is on still? Yes. Sometimes I need to get it refreshed. No, I shouldn't. I'm sorry, I'm sorry. Phone call is coming. Yeah, this 2.19 is not that easy. So it will seems to be a very easy problem, but I warn you that this won't be that much easy. it will have something hidden on it. So that's you to explore first. Solution is given. So I request you, when you start with it, go through the solution and try to understand how it's happening. It's a very standard problem. It came in jam, but it is, I guess, it's very old and very tricky problem in the mechanics, normal mechanics problem history. So, well, this is a set of very basic problem. I think this covered almost 70 to 80 percent of the different types of problem here. There are still some problem left which has not been asked in exams. So, let's see in the due course if I can discuss some different novel type of problems there. So, well, we go to the dissipative force problem. These are very easy. If you know it, then it's very easy. Generally we need to do a integration for this dissipative force problems. Let's have a quick review of that. Dissipative force problem. So it's generally as a frictional forces. I can have a little bit zoom here, no issues. So like minus kV square, etc., etc. So if something is going down, so we can say is, we always see it as Newton's law. So equate the forces, sorry, calculate the forces and equate it out with the mass into acceleration. So some particle is falling, and here it's the force mg and some frictional force kv. If this you take as z, this is z direction, it's always necessary to find to define your direction first. So then it will be m d square z dt square mg minus kv, or it's v is dz dt, so it will be mdv dt is mg minus kv, then integration. This is a very simple first type of problem. So there will be some v square, there may be gravity, may not be gravity. This is proportional to the square of the velocity, so this will be proportional of v square. So we will get this is again minus v square. So these are just repeated, all these problems are repeated. This is a viscous force problem, so this is actually the same problem, but it is better if you start with that Stokes law of viscosity, so then it would be better. Otherwise the final this t equals to infinity, the final result you need to address, you need to deal with. Okay, all these are I left to practice. So here this is that Stokes law, that if you better if you start this problem with this. So fine, this is a simple graph, terminal velocities, all these terms you will hear. This is a numerical, this is minus v problem, this is minus v square problem. So 2-3 basic problems, not 3 till now, 2 problems. minus kV problem and minus kV square problem. Sure. Will you do it? Just solution is there, so it is solved here. And my question is, will you do it by your hand? Please do that. Another part is another thing which I want to mention is generally you say a term always terminal velocity, which is nothing but v at t tends to infinity. So in the when the solution will be 1 minus e to the power minus something constant vagara. So this is when the velocity actually, this is when the velocity become constant. When this comes at when acceleration is 0. So we don't need to always calculate the exact solution to find the terminal velocity. Suppose we have m dv dt is mg minus kv. So when acceleration is 0, which means dv dt is 0, then here v terminal will be mg by k. So this is a silly trick. This competitive exam preparation is full of tricks. So this is the trick to get terminal velocity. Whenever you don't understand something, please have a pause, have a repetition. Ask your friend what side is telling. This is a crash course, so you don't please think that everything I will be able to teach here. So just have a quick go through. So well, you need to solve this integration. You take help from the solution and see what you can do. So then the next part will be for the second part. It is the basic Newton mechanics second part. Here it will be full with oscillatory problems. This is simple harmonic motion. So these files I will upload in the Google Classroom. I uploaded earlier also. If you have, then fine. Don't have, then join the Google Classroom. These are very simple problems. Have a basic review of simple harmonic motion anywhere, maybe from A.C. Verma. I will upload the slides also. Don't worry. Oscillation. I have a review from A.C. Verma. Simple harmonic motion chapter. Then why should I given this zoom? Does it serve any purposes? No, just to fill this gap. 106 is fine. Almost 100% done. Okay. 100 would have been better. Leave it. So have a review from H.C. Verma, and then you know this underdamped, overdamped, these things. There was the same equation with damping factors you studied in your graduation. So then the solution of that to the forced oscillation, damped oscillation. So you just go through a review. You don't need to go all the derivation, just result. And if you don't, then just do these problems. This is also, all these problems are easy. Conservative forces problem. Sometimes they will ask if a force is conservative or not. Then you know, right? at curl of f0, or that uh, if dot dr, this is 0, blah 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 blah. If dr is path independent, all these are same thing. If can be written as minus grad phi, that is a scalar potential. So these things are conditions, you might need it. I see this term conservative forces, so just I add this. This is a collision problem. We'll be doing this. Gravitation, attraction, correlation. This is very simple problem. This needs a concept of potential and potential energy. There is some disagreement on that. These are all easy. All these are easy. This might be a, this will need a concept of this centrifugal forces, mv square by r, but you will be able to do it, no issues. Okay, then this is also fine. Take a pause, look at the problem, try attempting yourself while you are watching the video. Make a pause, make an attempt, then tell me if you're getting or not. Answer keys will be there and the files will be uploaded in the Google Classroom, so don't worry, we have all the answer key solutions. So these problems, I don't think you will stuck anywhere. No solutions are big here. I have seen all this. Momentum is momentum conservation and variable mass. Center of mass, how to calculate. This problem is how to calculate center of mass, that you should know. This is nothing but to calculating the flux of the collection of the particles. Say many particles are going, how much momentum this is delivering in a, say, wall. So momentum transformation, I think you should know this. Sometimes it's not able to take the loads. Let's see. I'm sorry for the disturbance. Momentum transfer, just like a ball is hitting here, going there. So v and v, so that will be 2mv, the momentum change. That momentum has been transferred to the wall like this. So from here you will be able to calculate the pressure. So many particles are going through, and this is just, there is just a wall. See, this is a wall. I should have been drawn in a different way. Say this is a wall, particles coming back, particle going, particle coming back. So each and every particle got 2mv transferred in the wall. So then how much the momentum transfer will be for in a second. So you'll see that this is not a very tough problem. In 1 second, how much velocity flux will be transferred, how many particles will be there. So if you say in particles per unit volume, remember these things you calculated. And say this is a unit area or area A, you can see. So then in 1 second the length will be, I can change the color. So this L is V. In 1 second the particles which are 1 second the particle travels say 1 centimeter. So then the particles which are within 1 centimeter of that final wall, they will hit, others will not. Particle velocity 1 centimeter, say. So then which are 2 centimeters away or 1.5 centimeters away, after 1 second they won't hit. The particles which are within 1 centimeter, they will hit. So that this is a very standard calculation. You have done it in many ways earlier. So the total number of particles is n. This is a, say unit area or something. You can take the area A, then it's, you can take unit area A. So NAV, this is the number of particles. Then rest you think. This is the same problem, this is the same way we calculated the currents. That's J equals to NEV, the same way we calculated. So we can have this here. This is center of mass calculation problem. This is a very standard problem you should solve. This is a descriptive problem, but I always include this problem in my problem set uh, to check if you got the concept of this momentum transformation properly or not. That's not a momentum transformation, it's center of mass calculation problem. That if you don't have any external forces, so then your center of mass should not change, although the configuration might change. So listen again. If you have a system and in your system there is no external force, so then the system might adjust. System means you have means you have more than one number of particles, more than one number of elements there, 2 3 4 whatever. So you don't have any external forces, so the combination, so the position of the individual particles may change, but overall the center of mass of the system should not, because there is no external force. So this concept will be there. This is again a center of mass calculation problem, but there is a trick. I got it there. Chain problem. Chain problem is very interesting. You should at least solve your chain problems once. This is a very standard Erodop problem asked in just 2015. This is a standard variable mass problem. This 2.6, 2.7, all these are variable mass problem. If you don't know what variable mass problem is, then I have a note of that variable mass problem. I will send it in a Google Drive, this Google Classroom. So please go through this variable mass problem first. If you want to read it, please read from a book, then read from Kepner and Kolenko. I will write it down. First, this is also a variable mass problem. I just show you. This is a combination of variable mass problem and integration, so just check it out. This is a very tricky problem, very tricky. You will calculate a big, big calculation, but don't go through that calculation first. Try to think whether there is any trick on that. I also got this problem wrong, but me and Sandeep discussed, and then I finally laughed on ourselves that yeah, we missed it. So the answer key is not wrong, the answer key is right. So just think on that. So well, that much the variable mass problems asked in exam. There are more. So if you want to study a variable mass problem properly, so this variable mass, my notes you read, Klipner, Kolenko's book you read. So I will end today's class here. Next class we will discuss angular momentum. We'll have short classes, maybe in Saturday, maybe uploaded in Saturday, Sunday. So I will try to sit with you, try to upload 2-3 videos at least in a week. So then how much will be covered, I don't know. 8 weeks, 16, 24, yeah. I don't know how much I'll be able to cover, but please have a start. So let's see how much energy I get, how much feedback I get from the students. You like these things or not? Please give me a feedback. Always give you a feedback. You don't phone me, so if you always call me, then I will be very busy to attending all your calls. So get this WhatsApp number, get this email. I have this Facebook page, Facebook group, YouTube channels, you know. So okay, bye bye for today. This first class is I tried to be a little low and tried to contain my discussion very short so that you don't just get bored, but we'll discuss a lot, will increase our duration of the classes and contents as the time approaches, time of the exam approaches near. So next class within 2-3 days. Today is Friday, not Friday, yeah, yes, 12 past. So this is Friday. So let uh, let the next videos tomorrow, Saturday at most, Sunday. Well, bye bye. Then have a nice day. Please start solving problems and join with Google Classroom with this code. Okay, I will upload the contents there. Thank you. Thank you.